computation, and then show you some timing results and compare it to the old implementation, to the current implementation. And I would like to conclude showing you how to implement your own prior in this new setup. So map reconstruction, I think everybody is very familiar with it, but just very briefly. As you know, the image estimate is optimized by maximizing the posterior probability. We have two terms, the likelihood term and the regularization term, which is the actual prior. Prior can be very general and encodes assumption about how the image properties and guides our reconstruction towards plausible images. This is in the end is the map objective function we use to optimize in such problems. So we will focus on a specific type of priors, which are the Gibbs priors. The Gibbs priors are those priors who are modeled with the concept of energy from physics. The idea is to assign an energy to the function p of x, such as the inverse exponential of an energy function, which we will call u of x. And the idea is that improbable images are assigned to a high energy value so that the probability is low. If we talk about Gibbs prior, there is a general expression we can use to write such priors, and is the following one. Can you see my pointer as well, or no? Yes. Okay, that's nice. Okay, so this is the general structure of the energy function for the Gibbs prior. I would like to give you some details about it so that afterwards we can understand what we're talking about. So first of all, there are two summations. The first summation is running over all the voxels in the image. And the second one, the first summation is indexed by index I. So when we refer to I is the central voxel we are running over. The second summation is running on the neighborhood of that central voxel I, on the neighborhood which is defined by Ni. Ni can be different, can be whatever you want basically, but this is just an image in 2D. You see that in this case the neighborhood is composed by 8 voxels. If we move on to 3D, the easiest neighborhood you can think of is based on 26 voxels. It's the first neighborhood, square cube, a cube basically. Then we have the potential function, and this is where it's a function from R2 to R. So basically it takes two voxel values, two voxels, xi and xj. Xi is the central one, xj is the one in the neighborhood, and usually symmetric, which means that the links doesn't know if we are on the central voxel or on the neighborhood. It can be swapped. And the way we define the potential function, we can encode different kind of Gibbs priors, as you can see in those examples below. And K is an image, basically has the shape of an image, and is used to give voxel-dependent weights. Of course, there are 2K inside the formula because one is to wait for the neighborhood and one for the central voxels, so that we can weight each link in a different manner. Last, we have the omega, JI. Those are distance weight, and they are proportional to the inverse of the Euclidean distance. This you can think as a kernel matrix, basically, which gives weights, because, of course, the voxel on the diagonal is going to be farthest from compared to the one on the right. So we need to weight them differently. So this is it. Okay. So what kind of computation do we need regarding priors in image reconstruction? Well, we need the value, the gradient, for example, and action sometimes. So this is just a few of the computation we are involved during image reconstruction. We will start with the gradient because it's conceptually easier to parallelize. So this is the analytical formula of the gradient, the first one. And as you can see, we don't have anymore the outer summation, and we just have each component of the gradient is given by sum over the neighborhood, basically. So to parallelize this operation, it's quite straightforward. We just say, okay, each core or thread, based on if we are working on a CPU or a GPU, compute one component of the gradient, basically. Then we store those values somewhere, and the gradient has, of course, the same shape of an image, so we return those as an output. Okay. Instead, to compute the prior value is actually less straightforward because we have to do two separate operations, basically. So as you can see, there isn't the outer summation and an inner summation. The inner summation, which run over index I, is just a component of the outer summation. So we first need to compute each of the internal sums for each central voxel, store it somewhere, and this we are going to see it's critical on GPU. Where are we going to store those results, those partial results? And then we need to do a second operation, which is to sum all those value we computed into a single scalar value, and this will give you the value of the prior. This is the Hessian times input, another kind of operation we need. This is easier. It's very similar to what we can do with the gradient. It's just a vector, an image-shaped object, so we can compute each component independently and store it somewhere. I want to focus your attention on the fact that to compute all those kind of stuff, we just need 4 objects right now. We just need the potential function value for the prior value, the first derivative of the potential function with respect to the central voxel, and the mixed derivatives of the potential function, the diagonal one, so derived twice respect to the central voxel, and the mixed one. Okay, so let's see now how priors are currently implemented in STIR. So all STIR priors currently in STIR are derived from a base class called the generalized prior, which is a very general class. It's an abstract class, so and also doesn't give an actual implementation for the priors. It's just an empty framework to fill. So defines the computational methods, such as compute value, the gradient, the Hessian, and all the preparation methods, but doesn't implement it. So this means that all the derived class, which are the actual priors, needs to implement by their own compute value, compute gradient, and so on. This means that there is some degree of code duplication between all the implemented prior, because as we see the slide before, if we want to compute the value for the quadratic prior, the relative difference prior, the loops are just the same. The only difference is the potential function we are going to use. Also, for the CPU version, they are not parallelized. So this means that are quite slow, and maybe we can improve on that side. On the GPU side, currently, to my knowledge, there is only one GPU prior, which is the CUDA relative difference prior. So we wish to have a general framework where we have all the priors implemented on CPU and on GPU. So this is the proposed design, the new design. So basically, we introduced two intermediate classes that derive from generalized prior. And those are Gibbs prior class and the CUDA Gibbs prior class. The Gibbs prior class takes care of the CPU-related computation and implement in a general manner all the computation needed for priors. The CUDA Gibbs prior, we will talk about it a little bit afterwards, but it's derived from the Gibbs prior and override the computational methods on GPU. This way, let's focus for a second on the CPU side. When we want to implement a new prior, we can derive it from Gibbs prior and define it as such, those 3 blocks. But those 3 classes now needs only to implement the potential function, because all the methods are actually implemented in the Gibbs prior, basically. To achieve this, we templated the Gibbs prior class on a potential function, which now belongs to the member of the class. And of course, the Gibbs priors now is parallelized. So all the loops inside the computing methods, the computational methods, are parallelized using OpenMP. Okay, so before moving on to the GPU class, I want to give you a brief introduction to CUDA for those of you who are not familiar with. So we will call thread, usually they're called thread in GPU programming, is the smallest unit of execution for a GPU. You can think as a core comparison to a CPU. And they are grouped into warp. The warp definition is hardware defined. I mean, we cannot change it. And each on modern GPUs, they are grouped as a group of 32. So each 32 thread composes a warp, and they execute the same instruction simultaneously. What does it mean? It means that they have to wait each other, basically. And so if we have some divergence means if you have like an if conditions where instruction can take a different path, we can have bad performance because the warp is executed in a lockstep, so they need to wait each other, basically. So instead, a block is another kind of collection of threads, but this is software defined. So usually a good idea is to use a multiple of the warp size, which is fixed. For simplicity, we can just think, okay, I choose my block size to be the same as the warp size. Block size can be manually chosen, warp size not. A collection of blocks represent a grid. So this is kind of the image you have to think about. When you think about the threads inside the GPU, there is the grid, which is a collection of blocks. Inside each blocks, we have group of threads. This will come in handy when we talk about the memory management inside the GPU. Another word is the kernel, which is simply a function. You can think it as a function, and it's the function that runs on GPU, basically. When we want to launch a kernel in CUDA, we just need to provide the grid and block dimensions and all the parameters needed for a function, basically. So this is a brief comparison between CPU and GPU. A CPU has few powerful cores, and instead the GPU has many simpler cores. We're talking about 1,000 or 10 of thousands on modern GPUs. So, but they are quite simpler. So the CPU, since its cores are so powerful, we need a way to move stuff closer to the cores before actually doing any computation. Otherwise, we would have some time gaps between each computation. This is the focus on CPU. We want to have low latency. It means that we want the core to be occupied as much as possible. We don't want any gap between instructions. So this is why we have a very complex hierarchy of cache memory to move stuff from the RAM of the CPU closer to the core before actually doing computation. Instead, on GPU, the cache system is much simpler. We do not care that much if a core doesn't work for a given amount of time because we have so much of them. So its focus is on high throughput, the amount of the data it can produce in a given amount of time. Another difference is the branch prediction instead of branch predication. This means that CPUs are works better at predicting if statement condition inside the code. So it can predict the if output of the next iteration based on history. If you can think of it as if we have an if statement inside the loop, the CPU will manage it much better than a GPU. Instead, the GPU usually take both paths in an if condition and just mask the wrong outcome. So basically, take both paths at the same time. In general, we can say that CPU are suited for a general purpose sequential workloads. Instead, GPUs, if you have a massive workload, it's best suited. So this is a little bit introduction to the hierarchy on GPUs. There are other kind of memory that I haven't mentioned it in this slide, but those are the main ones. So we have the registers. These are per thread. The scope of this memory is per thread, and it's the fastest kind of memory we have on the GPU. It's stored on chip, and this is the speed. When we say 1 clock cycles, it means the how many cycles the GPU has to do to access one memory cell in this kind of memory. So if you take your GPU, you check out the clock speed of your GPU, it will take 1 clock to access 1 register, basically. This is compile managed. It means that we cannot directly access a register from coding. It's likely cache on CPU. We cannot decide what we put inside. It just depends on how we write the code. Has a very limited capacity. It's very small, 1 kilobyte usually per thread, even less usually. Then we have shared memory, which is more interesting because this is memory that's shared among a block. So remember, a block is a group of threads, and all threads inside the block can access the same shared memory. This is still very fast, not as fast as registers, but quite fast, and can be programmable. It means that we can access it directly from code and has a limited capacity, of course, not very big, but we can use it to a certain degree. Then we have the global memory, which is the actual RAM, let's say, of your GPU. It's very big. It's the one you see in the specs of a GPU when you want to buy it. Its typical range is in the order of gigabytes. And it's, of course, the default location where we want to copy stuff from CPU or GPU. But of course, it's also the slowest. So there is a compromise to be made. So last one about GPU programming is CUDA. Some of you maybe already know it, but it's a computing platform and programmable model developed by NVIDIA, used to interact with your GPU to a low level. We can also, as we can see, we can interact with the memory as well, and extend C and C++ with the APIs developed by NVIDIA to manage memory usage, kernel execution, and so on. So this is the typical workflow of a CUDA application if we want to write something on GPU using CUDA. So first of all, we need to allocate memory on the GPU, create space on the RAM of the GPU, on the global memory of the GPU, copy the input data from CPU to GPU. Then we need to launch the kernel. We need to synchronize the device because the kernel launch in GPU is asynchronous, so it doesn't wait by its own that the kernel is terminated. We need somehow to tell him to wait for all the threads to have computed the job, copy back the result from GPU to CPU, and then finally free the GPU memory. This is each one of these bullet points corresponds to a CUDA API call, basically. So if you do those 6 steps, you have your CUDA application. Okay, so now how the CUDA Gibbs prior class is structured. So remember, the Gibbs prior is the OpenMP class with the parallelized methods. The CUDA Gibbs prior is derived from it. And basically, all the preparation methods are inherited from the Gibbs prior. We don't need to implement preparation methods and also setter and getter to GPU. It doesn't make any sense. But all the computational methods related to Gibbs prior are overridden and implemented on GPU using CUDA. Each method has its own kernel. So if we have 4 methods, we have 4 kernels inside the CUDA Gibbs prior. Then if we want to implement actually priors on GPU, we can just inherit from CUDA Gibbs prior, and as before, just implement the potential function. As we will see at the end of this presentation, the potential function between the CPU and the GPU version of the priors is actually the same. We don't need two different potential function. We just need one that can work on host and device at the same time. So when I say host, it means the CPU, and device usually it's referred to for the GPU. Okay. So okay, this is an example. Let's take, for example, the method compute gradient. Okay, it's a void method, so doesn't return anything. Takes as an input the current estimate of our reconstruction, and we need also to provide a gradient object, which can be empty, or it's simply a space where we want to save our output. So this is the typical workflow you need to do. We need to allocate the memory for the prior gradient and also image estimate on GPU. We need to copy only the image estimate on GPU, do our computation. So we launch the kernel, we do what we need to do, and then we need to copy back the prior gradient on CPU. And then we need to free the memory. So if we take a look at the original GPU implementation of the priors present in STIR, which is the CUDA relative difference prior, all of this is done when we call compute gradient. The compute gradient do all of this stuff. Okay. So in the CUDA Gibbs prior, instead, we try to pre-allocate stuff. So basically, the allocation of the prior gradient and image estimate is done in the setup. So in the preparation, when you call setup on your prior, it will pre-allocate all the object it needs for computing stuff, basically. And also then we have the compute gradient, which just do the copy and the kernel execution. And to free the memory, this is done in the class destroyer. To be general, since we need to use different kind of methods, at the end of the day, we need 3 image shaped objects: the current estimate, the input, and the output. This needs to be allocated. And 1 scalar to support all possible methods, because we need a scalar, for example, to compute the value, because if we want to compute the value, we need somewhere to store the final summation of the value. We need those 3 objects. If you think, for example, about the computation times input, okay, what we need to use such a method? Okay, we need the current image estimate, then we need an input image, and we need somewhere to store the output. So those are 3 images, basically. So this is done in a general way in CUDA Gibbs prior. Basically, we pre-allocate for 3 image shaped objects and 1 scalar output, so that we do this once and for all and not inside each method. Okay. Okay, so let's have a look to the value computation. So as I was saying before, this is composed of 2 operations. First, we need to compute the inner sum, which lives on index I, and it's basically an image. So for each image voxel, we have computed our sum over all the neighborhood. Let's call this inner sum AI. Now we need to sum all of the elements of the image. So how are we going to do this? So there is this problem. This is general in parallel computing. Let's say I have a vector and I want to sum all of its component to a given memory cell. I cannot do it straightforward because all the threads will try to write their partial sum inside the same memory cell. And we will cause a race condition where some of the threads will just encounter another threads before them, already writing into the memory cell, and will just stop the execution because the memory cell is occupied, let's say. So to avoid this, usually you can use atomic operation, where you just turn your problem into a sequential one, and you just basically say the threads, okay, just work just one by one and save your results into the memory cell. This is not, I mean, if we want to save thousands of partial value into a single memory cell, this is not such a good idea, because as you can imagine, we are turning the problem back to being sequential. So because all threads must serialize the access in memory. So there is a better approach, of course, and it's related to loading the partial values into shared memory and then perform a pairwise block reduction. I will talk briefly about it in a second. So what is a pairwise block reduction? So let's say, let's think about the block of the GPU for a second. Okay, let's say I've computed this value. Those are 16 values I have computed. Now I want to sum it. And I want to do this for all the blocks in my GPU. So the basic idea is this in orange are the threads, okay? So we have 16 elements to sum, but we're going just to work with half of the number of threads. And we're going to say only the first 8 threads do a pairwise reduction. So the first thread is going to take the first element, skip 8 elements, and take the next one. Sum those two and store it in the first value in shared memory. The second one will do the same. So we basically, at each iteration, divide by 2 the number of partial sum we need to do. So starting from 16, we go to 8, 4, 2, and 1. At the end of the day, we found our sum in the first entry of the shared memory. Okay, so now we have all the blocks have computed their own partial sum inside the GPU. We need a way to sum all the blocks. At this point, at least for the problem we were trying to solve, we can either copy those partial results back to CPU, because now they are quite small. It's no longer a megabyte object to move from GPU to CPU, which we are talking about kilobytes. Or you can use now an atomic sum, because the amount of elements we need to sum, it's small, okay? Brief comment on this. This is not the fastest algorithm to sum elements in a GPU. There are faster algorithms, but they are way more complicated. And let's say this one is quite straightforward to implement, quite easy, and it's good enough. Okay, now let's see some results. The timing I'm going to show you are performed on this spec currently. We have run 2000 run, and those are histogram basically of the timings. So we can see on the green, this is a run on the relative difference priors, because I can compare 4 different methods on the relative difference prior. So in the green, we have the single core on CPU, which is taking, this is the mode of the distribution, which is, I found, much more stable than using, for example, the mean, since when doing those kind of computation, you may have very long tails in the distribution that mask your mean. So the mode instead is quite stable. On the green, we have
sorry, Matteo, can I ask you a thing?
Sure.
So what is the image size in this example?
I have to check. Can I check it? I can check it afterwards. So I have to go inside the dataset. I don't have the...
Right, okay. Just to have an idea.
Sure, I can check it. At least. Yeah, it should be like a 10 million elements, basically. That's the order of magnitude, but I have to check afterwards. Okay.
So it's like 200 cube or something like that.
No, a little bit more. It's in the order of megabytes. It's I use the Vision 600 Thorax dataset. I have to check the actual. I remember I checked it when I was doing stuff. I forgot to put it in the slides.
Yeah, so the 200 cube is 7 megabytes, and 300 cubes is 27.
Okay.
But it's this order of magnitudes.
Yeah. This is magnitudes. Yeah. So as we can see, this is the in the green we have the single core CPU taking around 160 milliseconds. On the blue, this is the CUDA relative difference prior to compute the value. And on orange and the red, there are the CPU implementation, which is taking, let's say, a similar amount of time compared to, which is the fastest. It's 1.8 milliseconds. using both the pre-allocation stuff and the block reduction, because we are viewing the value, so block reduction can be used in this kind of computation. This is the gradient. Similar results, but now I can no longer use the block reduction concept. So we see just like 20-30% improvements compared to the compute gradient, the original compute gradient on GPU. This difference from 6 to 4.5 is just due to the pre-allocation, basically.
Sorry, can I ask again, how many OpenMP threads are you using? So you have 12 cores, and I calculated you're doing half of them in performance.
What do you mean, half of them?
So it's scaling like 6. So from the original CPU to the new CPU multi-threaded, you have a factor 6 or 7, which is half of the CPU cores. I'm just curious.
Yeah, but the code is not exactly the same also inside the loop, because boundary conditions are managed in a slightly different way. So it's not like just exactly the same loops, just parallelized. The Gibbs prior is slightly different. Shouldn't matter too much in performance-wise, but it's not just exactly the same loop with a reduction with Pragma.
So you're using 12 OpenMP threads.
Yeah.
If you didn't change anything, the stir default is to use slightly less than the maximum. So it might be 10 or 11, I don't know, but yeah.
Okay. Yeah. It's a default.
Yeah, I was just wondering, because we normally take half of the CPU cores as a number of OpenMP threads. Because in CT we have a massive amount of data, so I think data transfer is dominating, so we don't want to block the whole computation by data transfer.
Sure. Okay. So this is the Hessian times input. I cannot compare it to the original GPU implementation because it doesn't provide the Hessian times input method. So this is a bit on its own. And this is one of the new methods. We implemented 2 new methods. One of them is the gradient times input. So basically, it's the gradient of the prior with a dot product with an input. So this is the CPU and GPU performances of it. And this is a profiling of the whole CUDA Gibbs prior with some of the methods. It's missing some of them, but basically the take-home message is always the same, that the main bottleneck, these methods, it's the memory copy. And from now on, only minor improvement can be achieved by changing the kernel design. If you want to know those, where are those 30, 27, and 26% spent in the kernel execution? They are mostly spent in the memory access because the prior memory access is not contiguous, so we need to access the neighborhood. So this is why the kernel is the kernel main bottleneck, let's say. Okay, it's not about the computation. This is what I wanted to say. So I want to conclude with showing you how to implement your own prior. If you want to implement the potential function and just define your own prior, we need 3 files. This is going to provide you with the prior that is working on parallelized CPU and the GPU version as well. So I'm not going to go through every line one by one, but if you want more details about it, you can ask me. But basically, those is the CXX file. We have constructor, the default constructor, parameterized constructor. This can be customized if we, for example, are using the relative difference prior. There are 2 parameters, which are epsilon and gamma. We need to add to construct the prior. And then we need a template instantiation because this is a templated class. So the CUDA version, it's basically a copy. It's very similar. The potential function currently is implemented in the third file, which is the .h. As you can see on the left side, this is the definition of the potential function. You just need to provide 4 methods, which are the value of the potential function, the first derivative, and the 2 diagonal and mixed derivative. And then we have the class definition on the right side. The top is the CPU version. This is the first part is the way to make parsing work inside stir, is the registered parsing object when we state the name of the actual class. The second is the class which is going to be used during parsing. And the third one is the base class, which in this case is the Gibbs prior. And if you see here inside the CUDA version, we just change from inheriting from Gibbs prior, we are just going to inherit from CUDA Gibbs prior, basically. And also we need to implement the name, which is used for parsing. So this is it. If you want more details, just ask me. And this is it. If there are any questions.
Suggestion.
Sure.
If I think each one of the kernel operations are independent of the next one, so could you potentially create 26 images, because they're only a few megabytes each, and each one deals with a separate element of the kernel, and then you just do a sum across the 26 at the end? That could help with both the contiguous memory access as well as the computation.
So you want to divide the kernel execution in more kernels, basically? No.
Well, yeah. In fact, you have 26 1x1 kernels instead of one 3x3x3 kernel.
Yes, I think we talked about it, but isn't a little bit weird on the diagonal ones? Because if we move on to the X, if I want to, so let me go back to the, can I go to the image very quickly? So basically, if I'm moving on to if I want to compute the X stencil, let's say, and Y stencil, I can use transpose.
The sneaky way of dealing with the diagonals is you could do an X followed by a Y to shift your diagonal down to the center.
Okay.
Yeah. So that supposes you know something about the weights, which I guess at the moment we don't really. We wanted to keep the weights as general as possible. There are optimizations possible if you know that you only do cuboid weights and things like that, but we didn't go there. In my opinion, a 2 millisecond operation is fast enough, but
yeah.
It needs also to be maintainable, obviously. So, yeah.
Also, sorry, isn't this suggestion going to use more 26 times memory? Because that's not going to be a good idea, I think.
Well, it's fine if it's 10 megabyte images, but not more than that. Yeah, sure.
Yeah. But also, I think, so I think this is all brilliant, right? The only thing that I was thinking of is how much, because you are holding the memory during the whole computation and also afterwards, right? So in an iterative algorithm, this is good because you don't have to reallocate and deallocate every time. However, then you'll take a share of the memory. So maybe for PET is fine with 300 cubed images. But I don't know with total body PET, what is the size of the images? And this will start to become a burden, I guess.
So regarding what Casper was saying, I want to comment on one thing. What I tried to do is but didn't work in the end, was to decompose the weight basically into links. So let's say, okay, I have a cube and it's 26 elements. My idea was okay, let's divide it into links such that I have basically a list of links, all the links possible. And then I provide the kernel or whatever it's going to use this object with just the links. Doesn't care much about the shape of the weights. But this was causing some trouble in memory access because it was no longer streamlined. Instead, if we call the kernel this way, it just, okay, it's a 3D array, but we streamline it to a 1D array, and the memory access is easier. And I tried, Edo, what you were suggesting a couple of months ago. You were suggesting like using an asynchronous memory copy, but it was taking slightly more time because I don't have the data here, but it was taking like 20% more time to copy the whole object, basically. So I was sparing time on the computation because it was happening at the same time. But if I time the whole memory copy, it was taking slightly longer.
Yeah, I mean, I have no idea. I'm never programmed in CUDA, right? So, but somebody Gemma in my group, she told me that yeah, I'm doing streams, and she could stream part of the data while she was computing. I have no idea what I'm talking about.
Probably it's.
Sorry, yes, kind of to add to that. Yes, exactly. This is, I think maybe in this case, not important because like 80% of the memory of the time is memory copies, right? So, you know, in some cases, I mean, it could be important, but basically, indeed, you can basically start copying while your copy and compute can happen at the same time, right? So basically, indeed, you can do that. But obviously, then the code becomes more complicated, right? Because you need to, in the streams, you need to be starting to wait for the other streams to make sure that the data is there and then the compute is there before, you know, and so on, right? So it is definitely something that will accelerate it. Maybe for this case, it's not that important because ultimately what you're going to do is we're going to overlap compute to memory, right? So, but memory is not going to become less of the time. Like it's not less amount of time. It's just the compute happens at the same time. So you are speeding up 17% or something like that if you go through that time, which is speed up. But you know you have a fairly good piece of code right now that is not super complicated. So I think, I mean, again, like this is super good work. So I'm not sure if that overcomplication will be worth it.
No, absolutely. Yeah. I even saw recently and Matteo that you can slow down your clock on the graphics card so that you match basically the data transfer. So if your computation is too fast, in your case, right, that's your case, you have 80% of the time it's taken by memory transfer and you have 20% of computation. If you were to do the overlapping of memory transfer and computation and slow down the GPU, that would be perfect. But
okay, maybe we can give some other people the opportunity to ask some questions.
Sorry.
Any questions from in the room here? Nope. Anybody else online? Just a comment from me on the memory transfer. Obviously, our aim is to avoid the memory transfer in the next version of Stir, where we are talking about using CUDA managed memory for all of the computations, because that memory transfer is, in this case, maybe not so important, but once you start talking about the measured data itself as well, then it becomes larger, right? And for the projectors, this is also a large fraction of what is going on. So certainly don't want to spend more time in optimizing the memory transfer here and streaming. I think for software like Stir that needs to survive another 25 years, it can't be too complicated. Yeah. Any other comments that people want to raise?
Perhaps got one. Have we settled on symmetric energy functions?
Right.
Is there any way for extending it? Or is that just a choice that's been made for kind of compute efficiency?
I tried with the links. The links was a good idea in my head too, but
yeah, I thought that was
was quite slow in the end. So
sure. Yeah.
So I think if you do the sum over both neighbors as in the original Gibbs formula, I think if you start off with something asymmetric, you can always symmetrize it.
Yeah, the analytical form, I think it's fine. I mean, it just the factor of 2, I think it becomes omega yj plus omega ji, basically.
Yeah.
Yeah.
If that's what you mean, okay.
Yeah, and your omega, why would you not choose your omega symmetric? You know, then becomes quite weird. Because that's a local neighborhood type of thing.
Yeah. Something like a Bauer wouldn't be symmetric.
There is something called the asymmetric Bowser, but the asymmetric Bowser is not really a potential function. It's something that looks like a gradient, but it isn't. It's not the gradient of a function.
So I have to say that there's actually no function definition. Yeah, they've just got a gradient for it. Yeah.
So this stuff is only for things that are really functions. Otherwise, it's different.
Yeah.
But for some optimization algorithms anyway, just having something that looks like a gradient is not good enough. Yeah. Okay. Final questions? No. If not, I have a few reminders, but before I go there, I'd like to thank Matteo again for, first of all, it was very nice to, Marcus has a question, but anyway, very nice to have you here in UCL. It was not just on the coding side, so it was really good. And also amazing contribution. I think everybody, hopefully we can sort out the licensing stuff and then everybody will be able to enjoy your work. So many thanks for that. And then also for a great presentation.
Thank you.
Marcus, do you want to ask a final question?
No, I just wanted to applaud the presentation. It was very good. I just misclicked. Thank you very much, Matteo.
Thank you. Thank you.
All right. So then might just be good to remind people of a number of activities that are coming up. I might be missing some. I think the first is our STIR users meeting at the IEEE Medical Imaging Conference. We hope that, we're working towards, and it will definitely happen, that this will also be accessible for people who are not in Yokohama. So there will be online links and so on. So follow the STIR website, this information there. This code hopefully will be merged in STIR soon, and that will be part of a number of optimizations that we are putting into STIR and SURF to speed up the code, and that will be important for people who want to participate in our PETRIC 2 challenge, PET Rapid Image Reconstruction second version. That we optimistically think will open in November. And for those who did not participate in the challenge previous year, the challenge is you have reconstructions which is again going to use the relative difference prior, but on phantom data and with target objective function, you just want to have an algorithm that implements that as fast as possible using SURF and SIL and associated software. The difference this year is that the data will be much noisier than before. So and software will be faster. So hopefully it will make life a bit enjoyable. Then the next activity will be at the end of the IEEE Medical Imaging Conference. Quite different. We have the Emission Tomography Standardization Initiative, ETSI, who's organizing our third hackathon on PET standard file format for list mode data, where we're getting very close to sort of the final proposal for comments. And that hackathon will update our use cases to implement that, and hopefully also implement some converters from existing proprietary formats to the new open standard. So that's 2 days after the MIC, so you're all very welcome to attend that, clearly. Then somewhere in March, we have the AI for reconstruction for biomedical imaging symposium, which will be in London at ASIS aside from King's College London. Still to be decided where it actually is going to be, but it's somewhere around KCL. That's 2 days, and then after that there will be a 2-day hackathon as well, where we're going to try and pursue some of the things that you've heard about today, but then also make some progress in integrating this into PyTorch and then implementing some example algorithms, machine learning algorithms. So that's sort of a follow-up from a previous hackathon that we had with a number of different groups participating, so you're all very welcome there. One new group that will be present is the deep inverse people, who have a library for deep learning with inverse problems, and so we're going to try and cover that up with all the things that we are working on. So I hope many of you can make it there. Yeah, I think that's enough for announcements that we have. All of this should be on our Synergy website, and if it isn't, Edu and Casper will make sure that it is. So many thanks for attending. I hope you enjoyed it all, and feel free to suggest a talk or contribute to talk for us next time. Thanks all.
Thank you. Thank you all.
Chris, I think